Hello and welcome to this recorded e-learning module for designers targeting Xilinx programmable FPGAs. My name is Srikanth and I will be your instructor for this module. In this module, we will learn about making area constraints using PlanAhead tool. After completing this module, you will be able to make effective area constraints by adding Pblocks to your design with help of the hierarchy viewer, schematic viewer, and the timing report generator of the PlanAhead tool. The process of floor planning begins by dividing some or all of the logic in the design into groups and constraining that logic. The PlanAhead software provides the ability to hierarchically divide the design into smaller and more manageable physical blocks or Pblocks. These Pblocks can include logic modules and primitive logic from anywhere in the logic hierarchy. You can group critical or associated logic together into a single Pblock, which prevents logic migration, limits interconnect length, and reduces delay. Creating a Pblock results in an area group constraint that is written into the exported UCF constraint file. The constraint in PlanAhead reflect the assigned logic, specified ranges, and defined attributes. Some designs can contain Pblocks that are larger than 20% of the device area, but these cases are rare. If so, try to make 2 Pblocks from logic at a lower level. Area group constraint is a design implementation constraint that enables partitioning of the design into physical regions for mapping, packing, placement, and routing. The area group is attached to logic blocks in the design, and the string value of the constraint identifies a named group of logical blocks that are to be packed together by the mapper and placed in the ranges if specified by the place and route. If area group is attached to a hierarchical block, all subblocks in the block are assigned to the group. Once defined, an area group constraint can have a variety of additional constraints associated with it to control its implementation. The range defines the range of device resources that are available to place logic contained in the area group. In the same manner, ranges are defined for the location constraint. In this slide, we will learn to create a physical block or Pblock in the PlanAhead tool. The first thing you need is to select a level of hierarchy or a component in the netlist window. Right-click and select the new Pblock command in the pop-up menu as shown in the screenshot here. Similarly, you can create new Pblocks from the hierarchy viewer as well as the timing report viewer. The new Pblock command creates a new Pblock in the physical constraints view, but does not create a rectangle in the device view. You must pre-select logic for assignment to the new Pblock. If no logic is pre-selected, the command creates an empty Pblock. To create new Pblocks with or without pre-selected logic, select New Pblock from the pop-up menu. PlanAhead enables automatic Pblock placement using the AutoCreate Pblocks command. This method is used primarily to create top-level Pblocks to view the data flow of the design and to understand the relative size and relationship between the various logic modules in the design. Normally, the designer has some concept of the critical modules and circuitry in the design and begins floor planning with those modules. To run AutoCreate Pblocks command, from the horizontal toolbar, use the Tools AutoCreate Pblocks command. In the dialog box, review the options with which you can define the maximum number of Pblocks to create and specify the minimum Pblock size. If more modules exist than the total number of Pblocks specified, it will create Pblocks for the largest module. The device viewer gives you a graphical display of your design's floor plan with the resources used on the FPGA. You can now easily create Pblocks by selecting a portion on the FPGA. The vertical toolbar provides you with different options with which you can draw Pblocks and control the view of net connections and location constraints. You can display various types of information with the Pblocks properties view. To display or edit Pblock properties, select the Pblock and view the Pblock properties view. The Statistics tab of the Pblock properties view displays content information about the Pblock. The Physical Resource Estimates displays a chart of each resource type in the device. Similarly, the Carry Statistics displays the number of vertical carry chain logic objects assigned to that Pblock. It also displays the tallest carry chain assigned to the Pblock and the percentage of its height in relation to the Pblock height. The Clock Report view displays the clock signals contained in the Pblock as well as the number of clocked instances on each clock. The RPM Statistics view displays the number of relatively placed macros objects assigned to the Pblock. It also displays the tallest and widest RPM assigned to the Pblock and the percentage of its size in relation to the Pblock size. The Clock Region Statistics displays the utilization percentage of each clock region that the Pblock overlaps. The Primitive Statistics displays the number of each type of logic resources assigned to each Pblock. The Primitive Statistics displays the number of each type of logic resource assigned to the Pblock. The PlanAhead software has extensive logic expansion, selection, and highlighting capabilities. These capabilities can be used to validate that modules are suitable to floor plan. For example, logic modules that connect to logic throughout the device may not be suitable for floor planning, while tightly grouped and self-contained modules are suitable. Routing congestion and timing inconsistency can be alleviated by floor planning logic outside of the critical logic areas, preventing logic from migrating into the critical areas. Use the Show Connectivity pop-up menu command to identify widely dispersed routing and tightly clumped logic modules. Use Shift-click to select source and destination logic. Right-click and select the Show Connectivity pop-up menu command. You can use the Show Connectivity command to highlight or select a cone of logic from any source net or logic object. You can analyze timing results from implementation to drive the floor planning effort. You can use the path sorting and selection techniques available in Timing Results view with the imported trace report data. Imported timing results sort the timing paths on a constraint by constraint basis. When you select paths in the Timing Results view, the Path Properties view shows the details of the timing path. Because the placement was imported, the path is highlighted in the device view. The visualization makes it easy to understand how to take appropriate floor planning steps to improve the timing. You can view the critical paths with the schematic viewer by selecting the paths and use the schematic command in the pop-up menu. This helps you to visualize the levels of hierarchy in your design. Then analyze the logic modules that needs to be floor planned. Then create Pblock for that logic module. Use the Select Primitive Parents command in the pop-up menu to select the smallest modules containing all of the selected primitives. The Hierarchy view displays the hierarchical relationship of the modules and the relative sizes. The selected logic module displays in the Hierarchy view, which is useful to visualize the module location and relative size prior to floor planning. You can select modules directly from this view for floor planning. Logic selected in other views is highlighted in the Hierarchy view. You can easily select parent modules of the selected design. You can easily select parent modules of selected logic to floor plan. Use the pop-up menu Show Hierarchy command to view a selected module with this view. This will show only the size and does not show the signals that are connected between the modules. Likewise, after selecting a component, use the pop-up menu New Pblock command to assign the logic. This is an example using floor planning for timing closure. The design has been implemented with no area constraints. Only post-implementation timing numbers identify what logic is failing timing. After the design has been run through implementation and the design fails timing, load the results into the PlanAhead tool. The PlanAhead tool will display all of the paths that are failing to meet timing. This will give you an idea of which paths are failing. Note the hierarchical blocks that are part of the failing paths. In this example, the block RAM with the critical paths are spread out over more of the chip than they need to be. Floor planning can be used to generate a tighter placement. The timing problem occurs in the paths between block RAM. So these paths are now good candidates for floor planning. Start off by loading the critical paths into the schematic. The schematic will show which gates are involved in the critical path and in which hierarchy the gates are located. You can trace the logic around the critical gates in the schematic to see how the non-critical logic is structured. The floor plan should constrain at least the timing critical paths to the block RAMs inside USB Engine 1. So far, USB Engine 1 appears to be a good candidate for floor planning. If USB Engine 1 is a large portion of the chip, instead we would try to floor plan the 4 levels of subhierarchy that contain the critical path. To quickly determine which gate should be floor planned, look at the placement in the device view. The gates in the critical hierarchies are colored green. The gates in the non-critical hierarchies are colored yellow. In the critical hierarchies, there is high utilization of the block RAM. The non-critical hierarchies contain a lot of LUTs and flip-flop logic that can be placed between the block RAM. The entire hierarchy is approximately 20% of the design. Block RAMs are fixed into separate columns. So anytime you have a hierarchical component that uses more block RAM or DSP slices than are placed in one column. You may have timing problems due to routing to and from separate columns. Before floor planning USB Engine 1, examine the pinout and design connectivity. There are long routes to pins, so the logic will need to be placed near the pins. The figure shows the top level floor plan for this design. Pblock 1 is OK, as it is near its I/O pins. Pblock 2 is also OK. Pblock 3 needs to be centrally located because it is the most popular block, as it communicates with the other Pblocks the most. Pblock floor needs to be lower and closer to its I/O pins. Pblock 5 needs to be in the upper left corner of the die. This will put it near its I/O pins and next to the Pblock 3. Pblock 6 could be placed anywhere, but it needs to be next to Pblock 3. Note that if you are going to make all of these area constraints, remember to make sure that Pblock 3 touches with all the other Pblocks. If other Pblocks communicate with each other, it is also recommended that they touch. In the end, if you did not want to make all of these Pblocks and area constraints, you could possibly get by with just an area constraint around USB Engine 1. The implementation shows the timing errors were only in USB Engine 1. Then an area constraint for Pblock 5 will be done. The USB Engine 1 could also be placed in the upper left corner of the die, which would place the logic closer to the I/O pins. This design has two copies of the same component, USB Engine 1 and USB Engine 0. implementation has shown that there is a timing problem with USB engine 1, which will likely appear in USB engine 0 as well. You will need to solve the timing problem of each block separately. Consider both USB blocks as two separate timing critical hierarchies and floor plan each hierarchy separately. The final solution is provided as shown here. PlanAhead creates a construct that enables you to constrain any subset of netlist hierarchy to a region on the chip. They are created using the new Pblock and assign to Pblock commands. The Pblocks are turned into an area group constraint in the UCF to guide implementation, and they keep the levels of hierarchy to various regions on the chip. In hindsight, there could have been a few more questions that you need to explore, like identifying the proper pinout for your design. Identify the central logic that needs to be placed in the middle of the die. Ensure that the area constraints are touching properly without overlapping, and also ensure that the area constraints are used to place logic near dedicated hardware. In summary, Pblocks are used to create a group of logic blocks. Low-speed Pblocks can be cramped to over 90% utilization. Conversely, high-speed Pblocks should be filled slightly less to give the tools the best chance to meet timing. This can also be used to improve your device utilization. There are a number of utilities in PlanAhead software that can help you make good area constraints. Pblocks can be created using Hierarchy Viewer, Schematic Viewer, and Timing Generator Reporter. You can learn more about PlanAhead tool from Xilinx homepage. Just go to the PlanAhead location specified here to learn more about what is offered. You can also view PlanAhead recorded demos, access the 30-day license for PlanAhead, and review the user guide and other software documentation. There are also recorded demos that discuss how to improve design performance with PlanAhead design and analysis tool.